So, a very good morning to all of you. Hope you are all fine at your places. Today, I am here with you one video that is related to the Thevenin's theorem, in which we are discussing about the proof of Thevenin's theorem. See, the Thevenin theorem, the superposition, the Norton, these are all theorems that can be used to calculate the current or the voltage in a particular branch. As we know, for calculating the voltage or a current through a particular branch, we have number of ways, like we are using Ohm's law, by using Kirchhoff's law, by using mesh analysis, by using nodal analysis, and also by using theorems. Now, in this video, I will teach you about the proof of Thevenin's theorem, how this Thevenin theorem can be applied to any of the electrical circuit for calculating the voltage or a current through a particular branch. And also we verify this theorem for performance, or you can say that for a proof of Thevenin theorem, what we have to do, we take a circuit as shown in your figure. Firstly, we can calculate the current through a particular branch by using mesh analysis. And after that, we can apply Thevenin theorem to the same circuit and then calculate the current flowing through the same particular branch, from which we can calculate earlier by the using of mesh analysis. And after that, we can see, is your current through the Thevenin or the current through the mesh analysis match? If it is match, then the theorem is verified. Another way, we can reject the theorem. So, first of all, let me start. For Thevenin theorem, let us consider the circuit as shown in the figure. Now, here we have a circuit. In this circuit, you can see that we have a voltage source Vs and a combination of loads, that is Z1, Z2, Z3 and Z4. These Z1, Z2, Z3, Z4 are basically a load that consists of a number of resistors that should be connected in series or in a parallel. So what we have to do, we have to convert or calculate its equivalent resistance. And here we have this Z1, Z2, Z3, Z4. These are all the loads. Now, what we have to do, we will calculate the current through the load Z4 by the use of mesh analysis. And after that, we can again calculate the current through again Z4 by the using of Thevenin's theorem, and see our answers are verified or not, isn't it? So firstly, we can solve the circuit by using mesh analysis and calculate the current through Z4. Now for that thing, what do I have to do? I have simply apply the mesh analysis. As we know, the mesh analysis says the number of currents is equal to the number of meshes. Now in this circuit, we have two closed meshes. One mesh is comprised of Vs, Z1 and Z2, and another mesh is comprised of Z2, Z3 and Z4. So what we have to do, we have to calculate, I have to mark the two currents. Let it be I1 in the first mesh and I2 will be the second mesh. Now when I apply the I1 current in the first mesh, now I can apply the KVL. So as I can apply the KVL, so it will be minus Z1 into I1. The reason being, here we have to go from negative positive to the negative. There will be a drop sign. And after that, we have a plus to minus Z2, then minus Z2 I1. But at the same end, this Z2 had another current, that is I2, which is sign is negative to the positive. So here we have Z2 into I2. And after that, you have negative to the positive. There will be rise. Vs is equals to 0. After solving this equation, we have Z1 plus Z2 I1 minus Z2 I2 is equals to Vs. This is your equation number 1. In the same case, I can apply the KVL in the second loop. Now, when I apply the same KVL in the second loop by taking all the sign conventions, so you can get an equation that is Z2 I1 minus Z2 plus Z3 plus Z4 I2 is equals to 0. So we have two equations according to the mesh analysis. That is equation number 1 and equation number 2. Now I can solve this equation number 1 and equation number 2 by using of Cramer's rule. So what I have to do, I have convert this equation number 1 and equation number 2 in the matrix form. So here you get a matrix. Here we have a delta. That's delta will be your first determinant and your delta 2 is your second matrix. Now when you solve this determinant, you have z1 plus z2, z1 plus z3, z1 plus z4, z2 plus z3, z2 plus z4, and I mark this equation as x equation. In the similar way, I can calculate a del 2. Now for del 2, what you have to do, you have to replace your second column with your outside column. So that means here have z1 plus z2 upon z2, and here we have vs and 0. And again, I can solve this equation, so you can get delta 2 is equals to minus of vs z2. Now simply your I2 will be del 2 upon del, and here we have del 2 is vs z2 and del 1 is equals to z1 z2, z1 z3, z1 z4, z2 z3 and z4. The negative sign indicate. Now this is the equation, this is the current through z4, and this current is equals to I2 by mesh analysis. So I have write down this is the value of the current I through z4 by the mesh analysis. Now I have to check the answer by applying Thevenin's theorem to the circuit. Now what we have to do, now I can apply the Thevenin theorem to the main circuit, that is a given circuit, and this is the given circuit from where we have to calculate the current flowing through Z4 resistor. I think up till clear, you have clear each and everything. Now for Thevenin's theorem, we have a certain guidelines, we have certain SOP for solving the Thevenin theorem, and under this SOP, your number 1 point will be you have to treat the load from where you have to calculate the current. Now in this particular circuit, I am treating the load as Z4. Therefore, let the load resistance is equals to RL is equals to Z4. Step number 2, remove the RL from the circuit and make the open circuit terminals. And this is the circuit where I have opened the Z4 and the terminals will become as T and H terminals. And here we have RL is equals to Z4. Now what I have to do, we have to calculate the voltage across these open terminals. And for this voltage across open these terminals, you see there is no current flowing through Z3 because it is an open circuit. And we all know in a parallel circuit, the voltage remains same. That means if I calculate the voltage through Z2, that will be the same voltage across Z4. Now, for calculating the voltage across Z2, we have to calculate the current through Z2. Now, I can do simply applying the KVL, and after that, I can calculate the current through Z2 will be I1 dash, which is equals to Vs upon Z1 plus Z2. And therefore, the voltage across VTH, that is the open terminal, is equals to the voltage across Z2 terminal. So that means your VTH will be equals to Z2 Vs upon Z1 plus Z2. Now, as I have already explained to you, for applying the Thevenin's theorem, you are required in the two main things. Firstly, the VTH, that is Thevenin equivalent voltage across the open terminal, and second is equivalent resistance between the open terminals. Now, as such, we are calculating the voltage across open terminal, that is VTH is equal to Z2 into Vs. Now, next task is our calculate Thevenin equivalent resistance across the two terminals. So for that, I can replace voltage source by short circuit, and here you can see that your Z1 resistor and Z2 resistor are in parallel in series with Z3 resistance. Now when two resistors are in parallel, we know the equivalent will be product upon sum. So that is why what I have to do, that is RTH is equals to Z1 Z2 upon Z1 plus Z2, and this whole combination is in series with the Z3. So that means that the combination of Z1 and Z2 is in series with Z3. So that is why Z1 parallel Z2 plus Z3. So here RTH is equals to Z1 Z2, Z1 Z3, Z2 Z3 upon Z1 and Z2. Now we have calculated the two main things, that is a VTH as well as your RTH. Is it clear? Okay. Now, lastly, what I have to do, we know the Thevenin equivalent circuit. This Thevenin equivalent circuit is comprises of your VTH in series with RTH in series with RL. Now, I can substitute the value of VTH, RTH, and RL and calculate the current through RL. So here VTH is equal to Z2 Vs upon Z1 plus Z2. RTH is equal to Z1 Z2 plus Z1 Z3 plus Z2 Z3 upon Z1 plus Z2, and your RL will be Z4. Therefore, the current through RL, that is Z4, simply given by the Ohm's law, that is I is equals to V by R. So here V is equals to Vs Z2 upon Z1 plus Z2, and R will be the sum of these two resistances. So that means Z1 plus Z2, Z1 plus Z3, Z2 plus Z3 upon Z1 plus Z2 plus Z. So when I solve these values, you can get I is equals to Vs Z2 upon Z1 Z2, Z1 Z3, Z2 Z3, Z1 Z4, and Z2 Z4. And this is the current through the load resistance RL. The same current we can calculate with the help of the mesh analysis, and you see at the end the current through Z4 using mesh analysis as well as using Thevenin's theorem is exactly same. So we can say that your Thevenin's theorem is verified. I think this will be clear to all of you. So you must watch this video carefully. And if you have any comment or any suggestions related to that video, you can comment me in my comment box. Your comments, your suggestions are always welcome you. So thank you so much for watching this video. I will come with another video where we are discussing about the proof of superposition theorem as well as the Norton theorem. So up till that time, thank you so much for watching this video. Thank you.